Assalamu alaikum everyone. Today we are going to conduct lecture number 11 for this online course, and today we are going to conclude our topic stake segment, and this is lecture number 3 specifically on this topic. We have conducted two different lectures before this lecture about this stake segment and covered their conceptual benefit and the basics about stake segment. Today we are going to see different examples from the textbook in which we are going to see the real scenarios in which we will be pushing and popping out different values from the stake. So let's proceed to the uh, topic. This slide is taken from the last lecture we covered. It provides a summary of what we have learned so far. So let's just go through it. So very first point is about stake. That is the basic of stake. Data is always stored onto the stake sequentially but in opposite direction. For example, if normal storage on code segment is basically happens in the direction from 00 hex to 5 times f in the hexadecimal, so there will be totally opposite direction for the stake. So this time stake will be flowing through ff to 00. This arrow also indicates this reverse direction. Second point which we learned about stake, it's very important point. The first word location in the stake is never used. That means these 2 bytes they never used. Let me highlight them. These 2 bytes never used in a stake. So whatever the information is going to store inside the stake, it will be stored from this location, these 2 locations. Okay. The next point we learned about stake, the logical address of the last word stored into the stake can be calculated by using two different registers, SS and SP. SS provides segment based address, SP provides the offset address for the stake. Then we learned 3 different terms about stake. First of all, bottom of stake. This is the bottom of stake where we learned that this location is never used for storage, but this is the bottom of stake because onto this bottom different values are gonna raise. And logical address for a stake pointer is always equal to FFE, as we can see here for the bottom of stake. Similarly, end of stake is a position up to which we can fill this stake. So this is basically SS colon 4 times zeros, and that means 4 times zeros will be the value for the stake pointer for end of stake as it is written here. And these 2 values for stake pointer specifically for bottom of stake and end of stake remains constant, they never change. Third important term that we learned about stake is top of stake, and top of stake is something up to which we have filled our information in stake. That means the top floor up to which we have filled stake is basically top of stake, and stake pointer is quite variable. It can be very close to the bottom of stake, it can be very close to the end of stake, it can be equal to the bottom of stake, it can be equal to the end of stake. So that is why stake pointer in case of top of stake is variable. Whenever stake is full empty, that means we haven't stored any information yet. So bottom of stake will be equal to the top of stake because we haven't filled information inside the stake. And in case of full stake, that means we have filled up to the last point, that is the end of the stake. So top of stake will become equals to the end of stake. That was the summary from the last lecture. Let's proceed to the next slide. Okay, this slide is also included from the last lecture because these are important facts. So, and we are going to conclude this lecture today. This particular topic. So that's why I also included this slide. So we learned 2 different ways in which we can push the data onto the stake. Word push is used to store the information onto the stake. Word pop is used to retrieve the information from the stake. These are the 2 terminologies. So there are 2 different ways in which we can push different data onto the stake. Number 1 is call instruction. Whenever call instruction is executed, the logical address registers, which are basically code segment and IP, automatically pushes onto the stack, so that microprocessor can actually track the previous program in which it was working before subroutine was called. The next way is basically subroutine, and in subroutine one can use push and pop commands to store certain content onto the stack. That content can come onto the register from any register, or can also come from memory. We are going to explore certain examples once we are going to deal with stack in the programming, and we have learned some examples of push and pop in last lecture. So if any one of you have missed those examples, please go through them. They actually explain it very well. One more thing that we learned is about return statement. Return statement or return instruction is always used at the end of subroutine. It actually forces back the content of CS and IP which were pushed before subroutine was called. So those two values will go back to their original places, and microprocessor will return to the main program. So these are the main points which we learned in the last lecture. So let's proceed to the next information. Okay, this is the new slide, and we are going to talk about some new knowledge and some already developed knowledge. We are going to just spot them. Let's see. Segment based value in stake segment register is the lowest address in current stake. It is something which is valid for every stake. So remember these thing mind. Lowest address or starting address is always pointed in stake segment register. In case of code segment, it will be in CS. In case of data segment, it will be in DS. So this is something which is valid for every segment. Stake pointer and base pointer. We have so far dealt with stake pointer. We haven't deal yet about this base pointer, but these two registers are always used as an offset value for the stake. Stake pointer is very oftenly used, that's why we have seen some examples, but base pointer is used in very specific addressing modes once we are going to deal with different addressing modes. So hopefully we will deal with them. Logical address of last storage place used in stake is always equal to SS:SP, and that is also known as top of the stake, as we learned in the last lecture. So last address which is used in stake is basically top of stake. Similarly, at the startup, when we haven't filled any information in the stake, SP is always initialized with the triple FE, and remember that is the bottom of the stake, which actually provides the logical address offset of for the bottom of stake, right? Similarly, we have also learned about end of stake. End of stake is something up to which we can fill stake. So the last address which can be used, remember, last address which is used is top of stake. Last address which can be used is basically end of stake. So end of stake is kind of limiting storage position in stake. Okay, whenever data is transferred to and from stake, these are basically 16 bits. Remember, we have seen 16 bits means two different bytes of information. For example, if content of IP is going to store into the stake, then it is 16 bits information. And if CS is going if CS value is going to store into the stake or is being pushed into the stake, then it is also again 16-bit information. So every time data is pushed onto the stake, it is in terms of 16 bits. So every time data is pushed onto the stake, this SP is decremented by 2. For example, it is FFE, so next value of it will be what? F and -2. That means 14 minus 2 will become what? Become 12. So that will become C. The next value will be A. Next value will be 8. So every time you're gonna push some 16 value in onto the stake, that means a word is written into the stake, and SP is decremented by 2. So every time we are storing information, it is decremented by 2. Similarly, every time we are going to retrieve information, it will incremented by 2. For if it is here, so that means it is triple F8. so it will be incremented by 2, so that become a. Again, if we pop out any other value, so it will be incremented by it will be incremented by 2, so that becomes 12, and so on. So every time you gonna push something on a stake, it will be decremented by 2, and if you gonna pop out some information from a stake, so it will be incremented by 2. So remember, these two things, they are related with each other, and we gonna see in some examples as well. Okay, in this slide we are going to deal with an example which is from your textbook. So here we are seeing a textbook example in which we see stake is shown, and it is starting from somewhere at some point, we don't know, but we are going to find out their bottom of stake, their top of stake, and their end of stake as well. We are given with these information. We need to calculate a address of top of stake. Remember, this a is always used to point physical addressing, right? Whenever this a thing is basically shown up or pop up, you need to know, or you need to know that okay, we are required to calculate physical address of something, and in this case it is top of stake. So we will be calculating physical address of top of stake for this specific stake which is shown in this picture. We are also known stake segment value, which is 0105 in hex, and similarly we are also given with stake pointer value, which is 008 in hexadecimal. So we are given with these two different values, and we need to calculate physical addressing of top of stake. Let's proceed how we will do it. So logical address, first of all, we are going to make their logical address. So top of address, logical address is always combination of two register. One is segment stake segment register, and other is stake pointer. So ss colon sp, it is the form in which we write logical address. So we are given these values. Ss value is 0105, sp is 0008, and what we gonna do, we are going to just simply apply the formula about physical addressing. We know we have to multiply segment base address multiply by 10. Look, we have did it, and then add the offset value, which is 008 here. So if we do so, its address become 01058. 0 is just most significant symbol in hexadecimal, so it doesn't have any significance here, but it is 20-bit address, we can observe. So where is 1058? This is the location. So that is basically our top of stake, TOS. I believe you remember what is top of stake, up to which we have filled certain information inside the stake. So what is the last information which was pushed into the stake? It is this word, AABB. We're gonna further clarify which one of these is basically most significant byte and which one of these is least significant byte, just in a short while we will exploring it. Well, if one is going to ask where is bottom of stake, is either it is somewhere here or somewhere here, let's explore. So for bottom of stake, we should remember the stake pointer value is always triple FE. So a stake segment is given 105, and so we're going to apply the same formula on these values. So it will be equal to 1104E. That means it will be somewhere where it will be upwards or downwards. So it will be somewhere here, because it is 1062 and it will move 1064 and on so on. So we will reach up to 1104E. So bottom of stake is somewhere here in the top. So let me reduce it, and let me mark it that bottom of stake is somewhere up. We don't know up to what point we have to go into the stake, but the bottom of stake address is basically 1104E. So I hope you have understand the concept of bottom of stake here and top of stake. Let's proceed to what this example further asks to us. Okay, this is the same example, and we are exploring here uh, about top stake, bottom stake, and end of stake. We have already calculated top of stake, that is our top of stake, and we pointed it that is basically top of stake. EOS. That point somewhere up is basically bottom of stack. And remember, if bottom of stack is somewhere up, so end of stack will be somewhere downward. So let's find out where is this end of stack. So if we are required to calculate physical addressing for end of stack, then what we will do, we have to apply the logical address, which is always equal to stack segment colon 000. We're gonna apply the value of stack segment, which is 0105. 00 is default value for end of stack, so we will apply the formula, which is the translation from logical address to physical address, and we will receive this formula. So 0105 somewhere here. Yeah, okay, that is the point. This exact point is basically our end of stack. So that means we are very close to, we have filled the information in stack very close to end of stack, and we can further fill in the information. Let's proceed to this example. What further this example is helping us to explore. Okay, in this example we are trying to uh, mimic the effect of push AX statement. We see push AX and AX is shown, its default value is 1234 in hex. So we are going to push that value into the stack. What will happen once this push statement is going to execute? It says push AX. So AX, its argument in the value of AX, whatever the content is going to push onto the stack. But how? We see AX is 16 bit of information. It has two different bytes. That is our least significant byte, that is our high significant byte. So high significant byte will store on higher address and least significant byte will store on lower address. So we know that that is our current top of stack, and here information is filled, right? So next thing gonna place somewhere here and here. So what will happen? We know that, okay, let me clean that. Okay, we know that this is 1056, so that is the address of this location. And what is the address of this location? It will be 1057 because 1058 is above, right? Similarly, this address is 1050, so that will be what? 1055 because 1056 is above. So we're gonna fill this least significant byte into lower address and higher significant byte in the higher address. So 1056 and 1057 are the basically addresses in which we are going to fill. So 12 will go to higher address, which is here 1057. So 12 will be stored here, and similarly this 34 will go to the lower address, which is, so that is how we have filled our information. Let me clean the unnecessary stuff so that things become more easy for us to understand. Okay, what we have done, let me repeat again. 34 is the lowest significant byte. It will store in 1056, which is the lower address. 12 is the higher significant byte. It will store onto the higher address, on which is 1057. So that will be the result of push AX onto this particular or on this specific condition of stack. Okay, in last slide we actually executed push AX statement, and our top of stack was moved from 1058 to 1056 because since we have pushed certain information, our top of stack or stack pointer should be decremented by 2. That is what we have seen here. So what is given in this slide, we are asked to execute pop AX statement and pop BX statement, and we are going to execute them one by one. So pop AX, pop means we are going to retrieve information from stack. So whatever the last information stored into the stack is going to fill in this AX register. So last statement is 1234. Remember, the least significant byte is stored and the least on the lower address, and the higher significant byte is stored on the higher address. So this higher significant byte is 12, which is stored on 1057, is going to be the part of AX higher significant byte. So that means 12 will come up here and 34 will come up here. And with the this particular statement, what will happen, let me highlight whatever we have. This is no more here, this is no more here, so top of let me clean it. Top of stake will be here now, right? We have retrieve information from the stake, so it will increment from 1056 to 1058, and it is increment of 2. Now the next instruction is pop bx. So whatever the last information is stored in the bx in a stake is going to be the content of bx. So this is our higher byte, since it is stored at higher address, which is 1059. If you are keenly observing in the last slide, we have shown you that this is 1059 and this is 1058, so that means it is basically higher address. So bb will go to this higher significant byte, so that will come here, b, and that is our low significant byte, so or low significant address, so that means it will come up here, a, and since these values are also retrieved, so let me highlight them also. So these are no more here, so our top of stake will switch its position and it will again incremented by 2. So our now current top of stake is this data 8899, and the top of stake physical address is basically 105A. And so in this slide we have explored how pop statement works when we are going to deal with stake. Okay, Alhamdulillah, by the grace of Almighty, we have covered a very good topic of stake, but some very small questions which may arise in the minds of any student of microprocessor. So how many stakes can be there in 8086 or 8088? There can be more than one, definitely, because we learned about segmentation, that there can be more than one segments, but out of many segments only 4 segments are active at a time. Similarly, there can be more than one stake, but how many active at a time? So only one stake segment will be active at a time. And if we want to switch from one stake segment to another segment, what we can do, we have to just modify the value of ss. For example, in the last slide the value of stake segment was what, 105, right? And if we just simply change it to 106, so we will be pointing towards a whole new stake, which is not the same stake, and we can actually switch to that particular stake segment by simply modifying the content of stake segment register. So these are the 3 basic questions which may arise in anyone's mind, so I wanted to just answer them. Okay, that's it. That is the end of the lecture number 3, specifically on stake segment, and lecture number 11 of this online course. If you have got any queries about this stake segment, so please note them down. We are going to deal with them in online session. Thank you so much.